Hi, my name is Mike Hagenow, and I will be presenting work on human-in-the-loop corrections for Affordance template registration on behalf of me and my co-authors from University of Wisconsin-Madison, NASA Ames Research Center, and NASA Johnson Space Center. To enable asynchronous operation of robots, such as in space operations or disaster recovery, robots need to be aware of objects of interest and their corresponding properties. One method for specifying and parameterizing objects is affordance templates. When using this method, operators often manually position a set of interactive markers in order to locate instances of a known object within a scene. Once an object has been registered, the template defines relevant object parameters for interaction, such as state information, joint information, and limits. While this process can be very useful for planning interactions with objects, the current process of manually registering the locations of objects is slow and requires a large amount of user input to fine-tune the proper position of the object instance. We instead want to localize objects in a semi-automated fashion. In our proposed method, users select points of interest and the system will attempt to automatically determine both the appropriate model and pose of the object. When the system is incorrect, the user can make corrections either to the selected model or model pose in order to help the system correctly register the object. For example, consider the scene shown earlier. Now the user can simply select points of interest, and the system will attempt to automatically recognize objects. The system is able to correctly identify two of the objects without any intervention. When identifying the valve, the correct model is selected, but the operator provides a small correction to the orientation, which allows the system to successfully register the object. With this system, the entire registration process required only a few instances of user input. In this work, we present a method for semi-automated object registration using a combination of an automated fitting method and human corrections. The fitting is based on the iterative closest points algorithm, which is often shortened to ICP. The ICP algorithm iteratively solves an optimization to determine the optimal rotation and translation that aligns two sets of points. This same process can also be used to localize sampled meshes within a scene. To decrease the likelihood that the algorithm converges to local minima, we employ a random restarts process when fitting each model. To increase robustness to occlusions and partial views of models that are expected when using a point cloud taken from a single view, we also weigh the samples in ICP based on the distance between corresponding points in the model and scene sets. After the initial fitting, users are able to provide corrections to the model or pose of the object. Operators can cycle through models, which are sorted based on a likelihood constructed from the residual of the fitting process. Operators can provide corrections to the pose using a 6-dimensional input, such as a space mouse or virtual reality controller. After the user has finished corrections, the system performs an updated ICP fit based on the new pose. In addition to testing on fabricated point clouds, we constructed a task board of typical interfaces that might be found during intravehicular activities on the International Space Station. The board consists of 5 objects: 2 ball valves, 1 stop valve, 1 e-stop button, and a drawer handle. We captured a static point cloud of the task board using the Connect Azure and provided corrections using a 6D space mouse as a feasibility evaluation of our method. Even despite the poor image quality of the point cloud, the system was generally able to fit the models with the aid of the user corrections. In most cases, the model selection was skewed towards slender models due to skew from the image capture. We believe that including color information in the likelihood calculation could help to avoid this issue in the future. The average fitting time of the models was 4.8 seconds with a range of 0 to 4 required model changes. Our preliminary results indicate the potential of our human-in-the-loops corrections approach. When testing the 5 objects in a fabricated point cloud, the system required 0 model changes and only 1 pose correction to the ball valve. The tests on the Connect Azure point cloud underscore the importance of point cloud quality. We believe that continuing to improve the robustness of the system for expected image noise and skew will greatly improve the utility of the method. We also believe that it may be highly valuable to add operator controls to select new point cloud images when the view is insufficient for recognition, and to add user overrides to the automated refitting when the image quality is poor. In summary, we presented a method for human-in-the-loop corrections for affordance template registration. We demonstrated the initial feasibility of our method through tests with fabricated and real point cloud data. In the future, we plan to extend our fitting and corrections to include articulations of candidate objects, such as the angle of a valve, and to allow for generalization to different scales of objects. We also plan to run a user study comparing our method to the existing state-of-the-art and to perform situated tests of our method in robot teleoperation demonstrations.